In the 5B4 notes, we're going to talk about properties of trapezoids. So we've talked about properties of every other type of quadrilateral so far, and the last one we have to talk about are trapezoids. So we've already talked about the definition of a trapezoid. It says it's a quadrilateral with one pair of parallel sides, exactly one pair. So we can't have more than one pair because otherwise we would have a parallelogram. And we call these parallel sides the bases. So over here I want to draw a picture. Trapezoid. We got our parallel sides I created by using either side of this straight edge. So here are my parallel sides. We call these the bases, so I'm going to highlight bases in green. So it doesn't matter how this trapezoid is oriented, the bases are always the parallel sides. So in this picture, a couple things we can label. Let's label this A, B, C, and D. We know that AB is parallel to DC. We know that the bases are segments AB and DC. And then we also have a couple more vocab terms that I want to talk about. The non-parallel sides we call the legs. So these guys right here are called the legs. So segments AD and BC are the legs. Let me highlight this guy. Bases again are in green. And then we call these angles base angles. So we have pairs of base angles. So let me get another color. I want blue. So I'm going to mark in blue all the interior angles. So this angle and this angle are called base angles. And then we have this angle and that angle are also base angles. So I'm not marking any of these congruent right now, but they are called base angles. So angle D and angle C are base angles, and angle A and angle B are base angles. So I'm going to highlight these guys in blue. So if we use what we know about trapezoids, using the fact that the definition of the trapezoid is we have one pair of parallel sides, if we look at this, we know parallel sides gives us some relationship with angles. So think through right now, what could you say about these angles knowing that these two sides are parallel? Well, hopefully we're saying that angle A and angle D are supplementary. So angle A and angle D are supplementary, and we can also say that angle B and angle C are supplementary. There's something else we can say about the angles that maybe you thought of, is that, and it doesn't have anything to do with this being a trapezoid, it has to do with the fact that a trapezoid is a quadrilateral. So if we think through what do we know about trapezoids being quadrilaterals, or all quadrilaterals, and that's that the measure of angle A plus the measure of angle B plus the measure of angle C plus the measure of angle D is equal to 360. So we know all of these things, and these will become helpful as we start solving problems involving trapezoids. Now, these are just trapezoids. We also have isosceles trapezoids, which is our special kind of trapezoids. Now, we've seen the word isosceles before. Isosceles in the past means that we have a triangle with at least two congruent sides. Now, isosceles trapezoid, we have four sides, and then we're not going to talk about at least two congruent sides, but we'll talk about the legs being congruent. So if you look at the definition, it says if the legs of a trapezoid are congruent, then the trapezoid is an isosceles trapezoid. So legs being congruent gives us an isosceles trapezoid. So I'm going to try and draw that for us right here. This is the kind of trapezoid that we're used to seeing the most often. This is the kind of trapezoid that a lot of us saw in elementary school. I don't know if you guys use the different colored blocks, the wooden blocks of different shapes. I know that I did when I was in elementary school. And so that's the kind of trapezoid we're used to seeing. So if we still have the definition of parallelogram, we have these two sides are parallel. I'm going to highlight them in green still because they are our bases. And now we have these legs, and I'm going to mark these legs congruent because it is an isosceles trapezoid. So again, here are my legs. So the legs of the trapezoid are congruent. We have isosceles trapezoid. So if I label these here, X, Y, Z, and W, in this picture there's a couple things I know if this is an isosceles trapezoid. I know that the bases are parallel, and I know that WX is congruent to ZY. And when you have isosceles trapezoid, there's actually a lot of statements that we can conclude, or things we can conclude about isosceles trapezoids. And some of them may be pretty intuitive to you. So I want you to think through right now, just kind of brainstorm in your head, what do you think is true about isosceles trapezoids? There's going to be three things that we're going to talk about. One has to do with the base angles. So what do you think is true about the base angles in an isosceles trapezoid, meaning in this case angle W and angle Z, and in this case angle X and angle Y? Well, what looks to be true is that they are congruent, and that is actually true. So in your homework, which we might be doing in class tomorrow, page 548, number 37, is a proof for if a trapezoid is isosceles, then each pair of base angles is congruent. Let's switch this up. Sorry, I didn't realize we couldn't see that. There we go. Okay, so in this picture, I'm going to draw this trapezoid a little differently now. So I'm going to draw it vertically. So we have this guy. This guy's still an isosceles trapezoid, so let's draw this in. So if we have A, B, C, D, where these guys are parallel sides, I want you to finish the statement. If A, B, C, D is isosceles, then what can you conclude based on this theorem? Go ahead and write that down right now. Well, the base angles in this picture, if these are the bases and these are your legs, and I can mark them congruent because we know this is isosceles, then the base angles would be this guy and this guy. These guys would have to be congruent, and these guys would also have to be congruent. So what that means is angle B would have to be congruent to angle C, angle A would be congruent to angle D, and that's what this theorem says. There's something else that we can also conclude, and that would be the converse of this. So let's say we don't start with an isosceles trapezoid. Let's say you just know that you have an isosceles, or you have a trapezoid whose base angles are congruent. You can also conclude that it must be an isosceles trapezoid. So page 548, number 38, addresses the converse of the statement that we just said. So if a trapezoid has a pair of congruent base angles, then it is an isosceles trapezoid. So let's say we draw another trapezoid. We'll make it look like this. So here is your trapezoid. May not look really isosceles, but try and bear with me. So we'll say here are our bases again. We know it's a trapezoid. That's all we have to start off with. So what you're essentially saying is if this is QRST, if I was trying to prove this, I would be given that if QR is parallel to ST and angle T is congruent to angle S, we want to be able to prove that this is isosceles, and it's only going to be isosceles if QT is congruent to RS. So if you do number 38, this is what you're proving. You're going to start with this, and you want to prove that QT is congruent to RS. So it would be the converse of this previous statement. So again, here are our bases. You are given that a pair of base angles is congruent. We want to know, can you prove that these segments are also congruent? So that converse is also true. So then there's one more thing that we can conclude, and that would be about the diagonals. So what do you think you can conclude about the diagonals of an isosceles triangle? Well, if you said that they're congruent, you would be correct. So page 548, number 39 and number 43 address the conditional and the converse, but we can write this as a true biconditional statement. A trapezoid is isosceles if and only if the diagonals are congruent. Now, you might ask, why didn't I write this one as a, or these two together as a biconditional statement? The reason why is that this is talking about each pair of base angles is congruent, where you only need one pair of base angles congruent to prove the trapezoid isosceles. And the reason why is if you know one pair of base angles are congruent, these two have to be congruent, because we know Q and T are supplementary, R and S are supplementary. So if two angles are supplementary to congruent angles, these two angles must be congruent, which is why I didn't write this as a biconditional statement, because the converse, as long as you know that one pair of base angles are congruent, the other ones have to be congruent, which then you could go from there. So that's why I wrote these two separately, whereas this one I'm going to write as a biconditional statement. So when we do this, I'm going to draw in a trapezoid. Okay, so we have J, K, L, M. These guys are parallel. You're given that because we know it's a trapezoid. Here are your legs. And with isosceles, we know the legs are congruent, so we're going to mark these guys congruent. And we're talking about the diagonals, so let's go ahead and draw in those diagonals. And if you're going to do a proof, it's going to be easier to name this, so let's just name this angle P. So we want to prove in one direction that if JK is parallel to ML and JM is congruent to KL, that implies that JL, the diagonal, is congruent to KM, the other diagonal. So that's what we want to prove. That's going one direction. The converse, because we're doing if and only if, would be the other direction, so I'm going to draw the arrow this way as well. So when you look at this, not only do we see a trapezoid, but we should see other polygons as well. There's going to be some triangles in here. So your challenge will be, can you prove that these diagonals are congruent? And this is where we're going to go back to our Unit 4 proofs, because these diagonals are corresponding parts of congruent triangles. So you got to prove triangles congruent, and then you can prove that JL and KM are also congruent. So you're going to want to look for congruent triangles. So those are all the properties of isosceles trapezoids. If you flip to the back, there's a couple more things that I want to discuss, and that is the mid-segment theorem. So a lot of information about trapezoids. The first thing we got to make sure we have the definition of a mid-segment. So in order to talk about a mid-segment, let's draw in a trapezoid here. Alright, so we got this guy here and here. Here's a trapezoid, not an isosceles, just any old trapezoid. We have A, B, C, D. So in this case, AB is parallel to DC. Those are still our bases, so I'm going to keep highlighting those in green. And then we have our legs, which are going to be AD and BC. And I want to talk about the definition of a midsegment. So, a midsegment, I'm going to do this in yellow because I haven't used yellow yet. A midsegment of a trapezoid or triangle, so we'll talk about a triangle in a second, is a segment that connects the midpoints of its legs. So remember we said the legs are highlighted in pink, so we got to look at the midpoint. So if we have the midpoint of AD, I'm going to label M, and the midpoint of BC, I'm going to label N. If we use our definition of a midpoint, we can think about a couple things here that we can conclude about the midsegment. So I'm going to draw in this guy right there. This guy in yellow is our midsegment. What I want you to do right now is try and write down anything you think you can conclude about this picture based on what we have written. So hopefully you've paused the video, you've written down as many things as you can. I'm going to write them down now together. The fact that M and N are midpoints tells me that AM must be congruent to MD and BN must be congruent to CN. So the first thing I'm going to conclude is that AM is congruent to DM and BN is congruent to CN. That's just the definition of a midpoint, which is part of the midsegment. In addition, based on the picture, we see that these two guys are parallel, and what I think looks true and what happens to be true is that MN, the midsegment, is parallel to the bases. So, number one, that's just gotten from the definition. The second thing that looks to be true is that MN is parallel to both AB and DC. It's parallel to both bases. So the midsegment is parallel to both bases. And the last thing is actually not very intuitive in my opinion. But if you look at the lengths of AB and DC, what do you think is the relationship between this length here? Well, it's in between. I know this one's the shortest, this is the longest, and MN is going to be in between, and in fact it's actually the average of those bases. So when I say average, we can add those two together and divide by 2 to get MN. So a couple different ways we can write that is that MN would be equal to AB plus DC divided by 2, or you could write that MN is equal to 1/2 the sum of the lengths of the bases. That would be another way we could write that. So this is the third thing we're going to talk about with midsegment, is that the length of the midsegment is 1/2 the sum of the lengths of the bases. So we can use these facts to solve problems in the future. Now, I put in parentheses triangles here. This is also true for triangles. But we don't talk about legs in a triangle. We talk about legs in isosceles triangle, but this doesn't have to be isosceles. So I could just draw any triangle. Zoop, zoop, and zoop. Switch this guy over to make sure we can see it. So I can just take the midpoints of any two sides. So if we call this triangle A, B, C, and I take the midpoints of AC and call this D, and I take the midpoint here, it looks like it would be about there, and call that E. If I draw in that segment, I'm creating this such that this is true. And what we'll see is, just using those same three things over here, that by the definition, AD will be congruent to CD, and AE will be congruent to BE. Oop, not BC, BE. The second thing is also true, that midsegment is parallel. Now instead of to both bases, we only have one side, so We don't call this a base, we just call this the other side. So I would say that DE would be parallel to BC. And then finally, if we think about this, there's not two lengths that we can average. So what ends up happening is that this length is just twice this. Or this length is half of this, however you want to say it. So you could say that DE is equal to 1/2 BC, or just BC divided by 2. You could also say, or this is twice the length. So 2 times DE is equal to the length of BC, whichever way you want to think about it. We're not going to do a ton with the triangles, but I did want to show you that the same thing is true of triangles. So we just went through a lot of information. I want you to use all of the information on the front and back of these notes now to do these 4 practice problems. Try and reason through these, and then we're going to discuss these along with a lot of other problems tomorrow in class.